As we have seen, all objects emit electromagnetic waves, and we will soon see how this radiation arises. For a solid object, such as the hot filament of a light bulb, these waves have a continuous range of wavelengths, some of which are in the visible region of the spectrum. The continuous range of wavelengths is characteristic of the entire collection of atoms that make up the solid. In contrast, individual atoms, free of strong interactions that are present in a solid, emit only certain specific wavelengths rather than a continuous range. These wavelengths are characteristic of the atom and provide important clues about its structure. To study the behavior of individual atoms, low-pressure gases are used in which atoms are relatively far apart. Here we show a sealed tube that contains a low-pressure gas. When a sufficiently large voltage is applied to the electrodes in the tube, the gas emits light, a process that is identical to that which occurs in neon signs. When viewing the light with a grating spectroscope of the sort we encountered in Chapter 27, which disperses incoming light into its constituent colors or wavelengths, we find that, instead of the full spectrum of colors or a single color, the emitted light consists of a series of individual colors or wavelengths, as we see here. The assortment of colors is called a line spectrum because the individual colors appear in narrow bands or lines. Different gases have different line spectra. For instance, here we see the line spectra for neon and mercury. The specific visible wavelengths that the atom emits gives neon signs and mercury vapor street lamps their characteristic colors. It's interesting that we don't need a sophisticated spectroscope or optical analyzer to see atomic emission lines. All we need is a simple transmission grating, which is nothing but a piece of glass or clear plastic ruled with finely spaced parallel lines. Here we see a glowing discharge tube filled with argon. If we look through a transmission grating at just the right angle, we can see the emission lines. Here, blue and green are the most visible. Next is a neon tube, which is a bit brighter. The set of emission lines for neon is very different from that of argon. The simplest line spectrum is that of atomic hydrogen, and much effort has been devoted to understanding the pattern of wavelengths that it contains. Here we show in schematic form some of the groups or series of lines in the spectrum of atomic hydrogen. The first series, on the low wavelength side, is called the Lyman series. It had been found empirically that the wavelengths in this series can be calculated from the formula 1 divided by lambda equals r times 1 divided by 1 squared minus 1 divided by n squared, where n takes integer values 2, 3, 4, etc., and r is called the Rydberg constant and has a value of 1.097 times 10 to the 7 inverse meters. The next series is the Balmer series, the wavelengths of which can be calculated from 1 divided by lambda equals r times 1 divided by 2 squared minus 1 divided by n squared, with integers n starting with 3. Next is the Paschen series, where 1 divided by lambda equals r times 1 divided by 3 squared minus 1 divided by n squared, with n starting with 4. The Balmer series is in the visible range. An essential feature of each group of lines is that there are long and short wavelength limits, with the lines being increasingly crowded toward the short wavelength limit. These equations are useful because they reproduce the wavelengths that hydrogen atoms radiate. However, they are empirical and provide no insight as to why certain wavelengths are radiated and others are not. It was the Danish physicist Niels Bohr who provided the first model of the atom that predicted the discrete wavelengths emitted by atomic hydrogen. Bohr's model started us on the way toward understanding how the structure of the atom restricts the radiated wavelengths to certain values and set us on the road to quantum physics. In 1922, Bohr received the Nobel Prize in Physics for his accomplishment.